Good evening, all, or I guess whenever you're watching this. If you're unfamiliar, my name is Dustin Newland. I'm making a series of videos just for a recitation I'm leading for IUPUI, just to support the students as they learn calculus and continue to grow in their understanding. So with that, we'll go ahead and hop on in. So for this video, I was wanting to real quick, well, as long as we need to, of course, discuss the Fundamental Theorem of Calculus. So, I wanted to make a video kind of detailing a little bit of the reason of why we have the things that we do and how we know that it works to be able to justify our use of it. Okay, so this video is purely just made to kind of prove this concept, but hopefully give a little bit of understanding into everything else that goes into it as well. So, with that out of the way, we'll get right into this. So, to start off, I have the first part of the Fundamental Theorem of Calculus written, which there are two different parts. The first part says that if f and g are continuous functions, and we let g of x be defined as the definite integral from 0 to x of f of t dt, then g prime of x is equal to f of x. Basically saying that the derivative of this g function right here is simply our function f inside the integral, but I just take the x and I put it in, okay? So this statement is basically giving us a relationship between what's on the outside of the integral and what's on the inside. So we can have a good understanding, a good grasp of how to connect these two pieces together, okay? So we're going to go ahead and get this proof here started. As you might notice, I have a picture already drawn, okay? Just kind of to give us an idea of what we're looking for, right? So g of x, right, is generally going to be this area underneath our curve, which in this case, this is my function f of x. It gives us the area underneath the curve from 0 to a certain x value of my function. Okay, so that's what this is saying, and so this is kind of the mental picture we want to think whenever we're talking about this, right? So, as with any good derivative problem, right, I don't have any fancy tricks to use on this, so what we're going to need to do is we need to appeal to the limit definition of the derivative to find this, right? Because if we want to figure out what the general rule of this derivative might be, we obviously need to go back to the basis and kind of build from there. So let's talk about that real quick. So recall, that f prime of x, so this is the derivative of a function, is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so this is the limit definition of the derivative, which comes from the fact that if I have two x points that are a distance h from each other, and I subtract their function values from each other, that if I take the limit as that distance becomes 0 of these 2 points, then this will give me the value of the slope of the tangent line at that exact point. Okay? So we're calling that f prime of x is this limit. Okay? So what we're going to do, right, is we're wanting to find g prime of x, right? So to find g prime of x, what I'm going to do is we're going to we'll come back to the limit later, but let's instead focus for now on what's happening with this f of x plus h minus f of x over h term, right? This is what's called the difference quotient, which you have seen before. So I need to see what's happening with this piece in relation to my function g, right? So what is g doing in this case? So if I replace f with g, right, I'm going to get g of x plus h minus g of x all over h. Okay? Because I want to see what that's going to do, right, before I can take the limit of it officially and see what happens. So, well, what do? Well, I take the values, right, and I plug it into whatever g of x is, which is g of x is defined as this function, right, that I have up here. So, notice g of x is simply what I already have, okay? So, I'm going to have, and this will be all over h, minus the integral from 0 to x of f of t dt, okay? Now, notice where that x goes in here. It's g of x, and so we put x in, and so if I have x plus h, then I simply plug that in for x. So, we end up with the integral from 0 to x plus h of f of t dt in that case, okay? Now, if you'll permit me, I'm actually going to, real quick, rewrite this, maybe to kind of help us to see a little bit of a different color, right, of what's happening. So we have 0, and then x plus h, and then that's f of t dt, okay? So, now we're not just going to x, but we're going to x plus h, right? So whenever it comes to my picture, right, I'm going to create a point, we'll call this x plus h, and so now what I want is I want the integral from 0 to x plus h. Right? So that includes all the brown space that I already had, and then it adds on this extra little purplish pink space on the right. Okay? But, let's look at this, right? So I'm basically saying take the purple pinkish color area and subtract the area of the brown part, right? Which, we're basically just looking at these areas and we want to see, well, if they ever touch each other, right, then those are going to cancel each other out because they're subtracting, right? Which is very noticeable in this specific range, right? Everything between 0 to x. We have a very clear crossover of brown and purplish pink. And so part of this area is going to cancel out, okay? And just to show that if the picture makes sense, that's great. I'm also going to show this using a little property we know about integrals. So I'm going to have us recall again that if I have the integral from a to b of f of x dx, or in this case we'll use f of t dt, then this is the same thing as the integral from a to a new number in between a and b, right? So notice a and b are upper and lower bounds. A new number in between them, call it c of f of t dt, plus the integral from c to b of f of t dt, right? Where, I'll write this, where a is less than or equal to c, which is less than or equal to b. Okay? Now, this is very clear. Just if we make a comparison to the picture, right? So in this case, our a is just 0, right? Our b is this x value, and our b is x plus h, and then c is our x value, right? So this is actually very convenient, very nice. To kind of see it picture-wise, right? I'm basically saying that the whole area of a section I'm given is just the sum of its split up areas, right? So if I take one part of the area and another part of the area, and I add them up, that gives me the whole area, right? So that's all this equation is saying, right? So now if we directly take this and apply it with what we have, that's going to tell us that, so A in this case is the number 0, B is our x plus h now, and A in this case again 0, C is now in between 0 and x plus h, so we're going to be focusing on x, okay, f of t dt plus, and then we're going to have x again to x plus h, okay? So I just rewrote this pinkish purple integral as the integral from 0 to x of f of t dt plus the integral from x to x plus h of f of t dt, right? Now take a look at what's going to happen, right? What do we have? We have the fact that if that 0 to x plus h integral is the same expression as this, and I take minus the integral from 0 to x of f of t dt, right, given us from the top, right, this integral here, a little bit circled not correctly, that's all right, and the integral here are going to cancel each other out nicely. So with all that being said, I'm going to erase this. And so whenever I take away this brown pinkish area here, right, because they're the same area so they subtract from each other, I am simply left with the expression that g of x plus h minus g of x all over h is equal to, now, if you'll permit me, this whole expression is over h, but that's the same thing as just writing 1 over h times whatever is left on top, which in this case we saw is simply going to be the integral from x to x plus h of f of t dt. And so we're left with this expression. Alright? Now, we're looking at this and it may not seem to help us, right? But we've kind of narrowed down our region, right, a little bit. Right? We're only focusing, we're wanting to see what's kind of happening in the x to x plus h range now, right? So that 0, or even whatever number I might have considered starting at, doesn't really matter to us anymore. All that I care about is looking at what's happening from x to x plus h. So let me redraw our picture slightly to make room for the particular area we're looking for. Okay. Once again, if I haven't mentioned it, the curve that I'm drawing, right, and when this, the axes I have here may not exactly be to scale, but all we're concerned about is here, not as much what's happening on the outside, but just kind of give us a little bit of a position. We're interested in seeing what the area is, what's going on with this area underneath this curve, right? The curve here may not be exactly what it is, what it's supposed to be, right? But I'm using this as a general picture, right? Notice that everything that I've done here doesn't specifically require us to know what that function is, but I do it merely as a picture to kind of see what's happening, because I find that helps many students to learn. So I'm here studying this integral at this point, so I need to think about this a little bit. So let's make a couple of observations, okay? If I take a look at my curve, right, you can see that in this case, in the one I've drawn, that it goes a little bit lower, right? right? There's kind of a section where it's at a low point, okay? And that's going to be kind of the minimum value of my curve on that interval. So I'm going to call this value, okay? I'll call this little m, okay? And this is going to be for some, I'll call the point x1, okay? So this is the same thing as f of x1, right? Because this curve that we have is f of x, right? So that little m, that minimum point that I have, is simply f of x1, right? What's going to happen if I, instead of maybe taking f of x itself, if I simply take that little m and I make a rectangle using that value, right, based on my interval? Well, I'm going to get a rectangle that's about here. Okay. So we get this. Now notice, it's just a little bit, in this case, and it might be more extreme in others, but in this case, we're a little bit below what the actual area should be, right? So what I'm seeing is that little m, if I make a rectangle using that value, actually gives me a box that's maybe kind of close, doesn't have to be, but gives me something that's smaller than the actual area, right? I can use the same sort of thinking to talk about, well, what about maybe a maximum value? So in this case, it looks like our maximum value is going to happen about here. I'll use a different color so you can see it a little clearer. We'll use this light blue. No, I think that'll clash. That's fine. We'll go with red. Okay? And we'll call this big M. Okay? Now, big M, it looks like, for the sake of just to help us a little bit, right? Let's suppose that, you know, maybe our curve dips down a little bit after that. So the actual value of this is going to be some, maybe x2, okay? Some x2 that's going to be before this x. Just maybe slightly before, we're not sure, okay? It could be x itself, but it won't be the same in any case. So I'm going to call that point x2, okay? In this case, I'm going to let big M, right? Notice if I'm using x2 to kind of give me that big M, then this is simply going to be whatever f of x2 is, right? Now if I make a rectangle based off that max point, right, just like I did the other time, so I use that as kind of like the height of my rectangle and use the x and x plus 8 bounds, notice that I actually get something bigger than my brown area in this case, right? So my brown area underneath my curve is, I can probably get a pretty good idea of maybe where it'll float at if I see what little rectangle and what big rectangle it's kind of bounding in between, right? Which to find these, I just look at wherever the minimum value is of my function on the interval and what the maximum value is on this interval, okay? And this has a general statement, so we're going to keep this statement in mind. And we're going to be using a property of integrals. This comes from a property of integrals, which I'm going to help us again. Let's recall this statement, which is that if I take the minimum value of my function, which I'll call little m, and I multiply that by the length of my subinterval, which will be something specific in this case, but in general, I can think about that as b minus a, right? Because that's the range that my integral is going to go from. This is going to be less than or equal to the integral from a to b of f of t dt, which is going to be less than or equal to, right? So remember, this is a small rectangle, and this guy is going to be a big rectangle. This is the red rectangle here. Less than or equal to m, big M, times b minus a, right? So whatever happens with my area, it's got to be bounded in between this little area over here, or this little rectangle here, and this big rectangle here, right? And we can see that from our picture, right? The brown area we're talking about is in between the smaller rectangle and this bigger rectangle, right? And this actually can give us some really useful information. So now let's plug in our specific situation, right? So in this case, A and B is x and x plus h respectively. So b minus a is the same thing as x plus h minus x, which just simply gives us h. How about that? All right. So what this is going to leave us with is we're going to have a little m times b minus a, which is h, is less than or equal to the integral from x to x plus h, right, plugging in for a and b, of f of t dt, and this is going to be less than or equal to big M times h. Okay, so we're left with this comparison. Okay, so I have a bigger value of m here, a smaller value of m here, and they're going to give me a smaller and bigger rectangle of which my actual area is enclosed in between. Okay? Now, this looks very close to what we just had, right? And I'm going to write down what we had, right, just in case anybody forgot, which I hope you wouldn't. We just had that on the last page, but g of x plus h minus g of x over h is equal to 1 over h times the integral from x to x plus h of f of t dt, right? As I said, this is very close, except we're missing one thing, and that's the 1 over h. However, I can get that really easy by taking everything in my expression and dividing it by h. So that's going to leave me, whenever I divide everything by h, right, I'm going to have that little m is less than or equal to 1 over h times the integral from x to x plus h of f of t dt. Suppose, let me rewrite that real fast. F of t dt, which is less than or equal to big M. Alright, so using their property that we had and dividing by h, I have something that's actually gets me back to the derivative I'm looking for, right? So what this means, when I replace this integral expression with the g of x plus h minus g of x, this is going to give me that little m is less than or equal to 1 over h. Sorry, the 1 over h isn't there anymore. Well, it is, but in a different form, right? This is going to be g of x plus h now minus g of x all over h, which is less than or equal to m. Okay, so what do we have? What is this telling us? What's the significance of what we just have? What we have here? This is telling me that this difference quotient of g from x to x plus h is greater than the smallest value of f of x on the interval, and it's smaller than the biggest value of f of x on the interval. Okay? Now, I don't want just the difference quotient, right? I need Dustin, I think what we need to do is to make sure that the thing's still recording. As you're kind of going through it before you finish the video. So, anyway, we'll go ahead and get back to this. Hopefully this is as close as it should be. I did make a little modification to this picture before we kind of move on here. Just kind of showing you a little bit more of the clear max and min, maybe give you a better idea of the rectangles, but the same idea still applies. So anyway, what I was saying is that I don't want just this difference quotient, right? I need to take the limit of that as h approaches 0, right? Take the derivative, okay? But I'm going to need to do that to every side.
So let's take our information here, what we have, and let's bring that up. Okay? So, right now, I have that little m is less than or equal to g of x plus h minus g of x all over h, which is less than or equal to big M. Right? So now all I need to do is I need to take the limit of this to get the derivative. So I'm going to do the limit as h approaches 0 of m, which is going to be less than or equal to the limit as h approaches 0 of g of x plus h minus g of x over h, which is less than or equal to the limit as h approaches 0 of big M. Okay, now, remember we actually had a rule which said that, you know, if a few, like, if functions are definitely less than each other at a certain point, right, then we can take the limit through, right? And so, as a reminder here, we're saying that our difference quotient is smaller than the smallest value of f of x on the interval and the biggest value of f of x on the interval. Now, what's going to happen as h approaches 0, right? We're not concerned much here. We know what this is going to turn into. But what is going to happen here and here, right? So, h, right, is going to start becoming smaller and smaller. So it's going to slowly come in and approach x, right? But, right, if I think about this, right, if I have my x1 and my x2 point here, right, and I'm bringing in x plus h, right, and I know for a fact, let's write this, right, that based on how everything is defined here, I'm going to need x to be less than or equal to x2, which is less than or equal to x1, which is less than or equal to x plus h, which I'll mention depending, you know, where your max and min is on your picture. These could be swapped, but I need these to be smaller than x and x plus h, right? So what's going to happen if I have those x1 and x2 values, right, and I take my x plus h and I say, okay, well, let's move it towards x. Is it just going to pass over these values? No, it's going to run into them and bring it along with them, right? Because what's going to happen, right, is I'm going to say as h approaches 0, we're going to get that x is less than or equal to x2, which is less than or equal to x1, which is less than or equal to x. Oh, and a reminder, these can be flipped, but it doesn't matter in this case, right? Because what do you notice? These values are both bigger than or equal to and smaller than or equal to x. So there's really only one possibility with them, and that possibility is that, well, x2 must be equal to x, and x1 must be equal to x, right? So, if we come back to our picture, if we remember that little m is f of x1, and big M was our f of x2, right, and we're considering the limit as h approaches 0, well, that brings those values down, right? I can kind of imagine that basically I have this eraser is this wall that's slowly coming in and bringing in the curve down and down and down and down and down until all that I have left of it to be concerned about is the sliver section that's at x. Okay? So, as I said, x1 becomes x and x2 becomes x, right? As h approaches 0. So that means that little m is just going to be the same thing as f of x. What about big M? Well, x2 is also going to go to x. So this is also f of x. What's this guy right here? That's the derivative of g, right? Remember, that was the definition. So we have that f of x is less than or equal to g prime of x, which is less than or equal to f of x. Well, we run into the same predicament again, right? Because if I'm bigger than or equal to and less than or equal to something, right, in this case being f of x, then the only possible solution is that I am that thing. Which leads us to conclude that g prime of x must be equal to f of x. Thus, ending the proof. Okay? Awesome. So that concludes it. One little note, a couple little notes I want to make mention of here. The first big one I want to say is that originally when we were doing the proof, right, or as we were going through it, we had this bottom value here is 0, right? But I don't have to let that be 0, right? Because you notice after we got to this point that whatever the value was to the left here, whether it was 0 or it was a, it didn't matter. The proof would work the same way. So even if this goes from a to x, right, some a value, some real number, right, that's the left point of an interval, then we're going to get the same exact result, okay? And this is going to be actually very important for doing the second part. Okay? So, we have our conclusion, right? Which, again, is just telling us that the area from 0 or from a up to x, you know, basically whatever this small area is, here, that formula for g of x, right, that may give us that area, the derivative of that g is simply just the function itself that we're finding the area underneath. Okay, now we get to move on to the second part. Alright, so we've got done with the first part, so check that off our list. We need to move on to the second part, which the second part tells us that if, well, actually we don't even need an if. It simply tells us that the integral from a to b of f of t dt or f of x dx, depending, this is the same thing as f of b minus f of a, where big F is any underlined antiderivative of f. Okay, well, how does this one work? How do we prove this, right? This is the second part of this guy, it must be long. Well, not really. The first part actually did most of the work for us. So, the second proof is actually a lot simpler. Because all I need to show, right, is that I can use any antiderivative to find the area underneath this curve, right? So we need to think about, well, what's one antiderivative I definitely know is for my function? Well, we know g prime of x is equal to f of x, right? That's from part 1, right? How does that relate g to f? Well, that means g must be an antiderivative of f, right? Because if the derivative of a function is the function we want, then that makes that function, in this case g, our antiderivative, right? So we're going to bring back g of x, as the integral from a to x, right? Remembering that a is just a change of, I can make a whatever I want rather than it being 0, of f of t dt. Okay. So, why does that matter to us? Well, let's take a look real quick. G of a, if I evaluate it, is the same thing, right, as I just plug in a into x, right? So I get a to a of f of d dt. Well, if you're not sure what's supposed to happen with that, let's recall real quick. I'll recall with a different blue. Recall that the integral, and this is any integral from a to a, of f of t dt, or f of x dx, since I'm going from one value to another, right, I basically have a box, right? I'm thinking about even just a box with 0 width, right? If I take a box with 0 width and I multiply it by a length, it's still going to be 0. Okay, so we're going to recall that one of the properties of our integral says that if I go from a to a for my integral, it's just going to be 0. And so that still holds true, and we get 0 for this, right? Now, g of b, I just take b and I plug it into my integral. And so that's going to be a to b of f of t dt. Hey, that's what we want. Right? Now notice, right, if I take g of b minus g of a, that absolutely gives me what I want, right? That gives me kind of what I'm looking for, right? But I don't want to just settle for g. I want to use any antiderivative, any possible antiderivative I can. So, we're going to go with the antiderivative f, right? Now, you should have learned at this point that every antiderivative, right, if I take two different antiderivatives of my function f, then they're going to differ by a constant. That is that if I let big F of x be an antiderivative, that is going to be equal to g of x plus some constant c, right? Where I'll write c is a real number. Okay? So this gives us a whole bunch of different options for big F of x, right? Depending on what I pick for c. But they're all going to be antiderivatives as compared to with the g, right? So let's talk about real quick, right? Of course, I need to figure out what my values are at f, right? To be able to plug in here. So what is big F of a? Well, it's simply going to be g of a plus c. But g of a, right, we already said was 0, so this is simply just c. What about big F of b? Well, this is simply g of b plus c. But I know that g of b is the integral from a to b of f of t dt. And then I add plus c on the end of it. Okay? So that is my big F of a, and that's my big F of b, right? Notice that it's very similar to here, except there's just a constant added. Now, what's going to happen if I take big F of b minus big F of a? Well, I'm going to get big F of b, which is the integral from a to b of f of t dt, plus c minus f of big F of a, which we said was c. What's going to happen? The c's are going to cancel out, right? And the expression we're left with is exactly the thing I was looking for, right? Because big F is any antiderivative of little f, right? And so we just showed that for any antiderivative of little f, right, which is, if I know g of x is an antiderivative, then big F of x, another antiderivative is just that plus c. That big F of b minus big F of a is equal to the area underneath the curve, right? So that's what we just found, and that tells us that if I know the antiderivative to my function f, then what that's going to do is I can find it, plug in b, plug in a, and when I subtract the two values, it's going to give me the area underneath this curve from a to b, surprisingly enough, which is really nice. So, just to demonstrate that, right, so recall just, let's say, I'll erase this. So let's say that we had a curve. Okay, we gotta make something simple. We'll do, let's see, we'll just do this line. Okay, so let's say I'm curious about this line from A to B. Well, the
antiderivative of this curve is going to look something like this. I'm going to get this parabola. Okay? That is the antiderivative of the line, right? We don't know what exactly it is, right? You could put some things on there to see, right? But that's going to be the value, right? So I'm going to make this, I'll probably extend this a little bit more this direction so we can get a connection here to B and here to A. Okay. So what this tells me is that if I call this little f here and I call this big F, now this can be any, but in this case I'm letting this be the big F. Okay? If I want to find the area underneath the curve from A to B, then I'm going to take big F at B, which is about here, we'll say, minus big F of A. So here we have big F of B, and here we have big F of A. And surprisingly enough, if it didn't seem clear like it would, whenever you subtract the two values, that difference is the same thing as this area. And so that gives us the what we're looking for. Alright, well, we just proved this, so let's put a big old check mark, and we've talked through it. But this right here is the fundamental theorem of calculus. Let's repeat it one last time to finish off. Number one, if f and g are continuous functions and g of x is the integral from a to x, or a where a could be 0, of f of t dt, then g prime of x is equal to f of x. And the second part says that for any antiderivative of big F of f, we have the integral from a to b of f of t dt. It's big F of b minus big F of b. Okay, so this is the fundamental theorem of calculus. Proved and explained. So, yes, thank you so much for watching. I greatly appreciate it. Hopefully, it's been nice to kind of run through maybe a little bit of review, but of course, there's a lot of new properties that are involved, right? But it's something that it's good to start wrapping your head around and start to understand that you can apply yourself whenever you're doing problems to be able to critical think more and be able to handle more and just, yeah, be able to do well in calculus. So, yeah, with all that being said, thank you so much for watching. I hope that you have a wonderful night.